All right, so welcome to Math 383, Complex Analysis. This is Lec09, and so what we're going to do today with integrating. And so we're going to talk a little bit about some of the reasons why we care about the integration that we're going to be doing, in particular talking about convolutions, Fourier transforms, integration examples, and then if time permits at the very end of class, we're going to talk about removable singularities, poles, and essential singularities. The definition of essential singularity is really nice. It's basically anything that's not the first two. So it's the extra bucket that captures everything else. So general items to be thinking about: if you have an elephant gun, it's not necessarily a bad thing to use it to just destroy a problem. But sometimes it's nice to see what's the simplest, most elegant approach you can do to prove something. So if you're proving a research paper, one of the dangers of using the most recent bounds is if a mistake is found in that paper, then all of a sudden your results might be questioned. And so you often want to say, what is the strongest result? What is the weakest result I need to prove my result? Not necessarily what is the strongest result known. Now, frequently people will just use the strongest result in the literature, but it's nice getting a sense of just how deep is the result. Do I really need this strong result, or do I just need anything towards that? There is more than one way to integrate without integrating. And so today we will see another way to integrate without integrating. So what's the first way we've seen to integrate without integrating? So we've seen bringing over good. So yes. So there's another one, but bring it over is definitely one.
Is it just zero?
Okay, so closed curve.
Yeah, integration by class.
Integration by class. But I'm thinking there's a formula that allows us to convert finding integrals to an algebra problem. The residue theorem, right? If I have a function that is holomorphic except for finitely many points inside a curve, then I can actually figure out what is the integral along the curve by just calculating the residues. And that's just doing Taylor series expansions at a couple of points. And frequently what will happen is your contour, one part of the contour you'll care about in the limit as the parameter goes to infinity, and the other parts you just use to complete it. And they don't really contribute in the limit. And this is a great way to get a lot of real integrals by just having them as part of a contour and the other parts not really mattering. So we're going to see other examples of this. Okay, so the first is to just do a little bit of motivation of why we care about some of these results. If you've taken probability, you've hopefully seen results like this. We may do a little bit more with the central limit theorem later in the semester. So the convolution is a nice operation. It takes two functions as an input and gives you a new function as an output. And so I've done it in both the discrete and the continuous case. We will focus on the continuous case here. So the convolution of fx and fy is the integral of fx of t, fy of z minus t. And then we're just integrating over t from minus infinity to infinity. Z is not a complex variable here. Z is just where I'm going to be evaluating things. And in a lot of really good applications, these functions fx and fy are probability densities for random variables x and y that are independent. And we might talk a little bit more as to why would this be the density of x plus y? Well, if I want x plus y, say I want x plus y to equal some value z, then if x equals t, what would y have to equal? Z minus t. And that essentially explains where this integration comes from, is I'm integrating over all pairs like that. So if I want the sum to be z, well, what's the probability that x takes on the value t? And then I multiply by the probability that y takes on the value z minus t. You can prove this more rigorously than that, but this is, I think, good enough for now. What can you tell me about the convolution of, say, fx star fy and fy star fx? They're equal. Why are they equal? So one is change of variables. There's another reason why they're equal. Yes. X plus y is equal to y plus x. Here. This is the probability distribution of x plus y. Well, that's going to be the same distribution as y plus x. So you could do the change of variables, or you could step at another level and say, oh, Well, this is useful if I then start adding 3 random variables or 4 and have a more expansive convolution. Now, this is also in a very special case where my f's are probability distributions. That means they're non-negative and they integrate to 1. The convolution can be defined more generally. And you can ask, for what functions can I take the convolution of, say, 2 functions f and g? And then if you want to prove that the convolution is commutative, then you would do the change of variables. You would lose the physical interpretation here. Okay. So when we are looking at convolutions, let me come back to that actually. How many of you have seen an integral transform? Okay, so an integral transform, not surprisingly, takes a function and gives you a new function by integrating. And so you have some function k, which is the kernel, and it's going to be a function of 2 variables. And then you integrate your function against this kernel, and it gives you a new function f. And so here I'm just going to call it k of f. If you've done Fourier transforms, it might be f hat. If you've done Laplace transforms, it might be L of f. Mellon transforms, m of f. Usually when it's a person's name, you just chop off everything but the first letter. So which k's are worth studying? That's the interesting question. Now, we also want to know when things are going to converge. So something we will be using frequently to prove certain spaces will be nice is the Cauchy-Schwarz inequality. And it says if I take 2 functions f and g and I integrate them, then the integral of the absolute value is thus equal to the integral of the square of f square root times the integral of the square of g square root. And so hopefully in real analysis, you've talked a little bit about LP spaces. Function is an LP of some space or set S if the integral of the p power is finite. And in terms of just making it nice, it's convenient to take the 1 over p power of it. If you think about units, it's a nice way to be looking at things. And so what will we want to look at? The main one we're going to want to look at is the Fourier transform. And we'll do a little bit more with that later in the semester. I'm just stating for definiteness the Laplace transform above. So the Laplace transform is defined by integrating a function f from 0 to infinity, and I hit it against with e to the negative st. So if you're thinking about what we had a moment ago, we have a function k of xy. Well, my function is just going to be k of st is e to the negative st. The Fourier transform is pretty similar, except I'm multiplying by e to the negative 2 pi I xy. So there my k of xy will be e to the negative 2 pi I xy. So who are my physicists again? Are you happy with this definition of the Fourier transform? Or what do you want to change? So you don't like the 2 pi up here. Okay. You like the 1 over square root of 2 pi? So there are 3 different, there's at least 3 different definitions of the Fourier transform. So depending on whom you're talking to, you could hear a slightly different version, and so you always have to be extremely careful. I learned spherical coordinates from the physicists before I learned it from the mathematicians. So whenever I teach math 150, I have trouble because I teach it like a physicist with my choice of theta and phi. I have to remind myself, no, I'm in the math department now. You've got to be careful when you look at things. There are a lot of good reasons for putting the 2 pi there. The putting the 1 over square root of 2 pi is trying to almost appease both sides. I'll do a little bit of each of yours and try to. But in terms of defining various things, there are benefits to each. Just be aware of what people are using. Do you think the Fourier transform and the Laplace transform are related, or did I just need stuff to fill up the slide? Can you see how to choose parameters to go from the Laplace to the Fourier or the Fourier to the Laplace?
If the Fourier transform complex, or Laplace transform of purely complex numbers.
Well, you don't take the Laplace transform of a complex number. You can evaluate the Laplace transform. So, right, so if you evaluate not at a real S, but if you imagine that S is imaginary, maybe S equals negative 2 pi I y, then all of a sudden you have the Fourier transform. So it's actually not that hard to pass back and forth between your Fourier transforms and Laplace transforms. Yes.
So even the in terms of variables of the negative infinity from 0, how does that?
So you've got to deal with some issues like this as well. But I'm just saying you should see that there's some similarities between them. That there should be a way to convert maybe from one to the other. And if you look at the definition of the inverse Laplace transform, it's given as 1 over 2 pi I, integrating from c minus it to c plus it as t goes to infinity. This looks a lot like the type of stuff we've been doing in complex analysis. So the point here is to show you that these actually have great use. How many of you have taken a class in differential equations? Okay, did you do Laplace transforms or Fourier transforms to solve problems? Excellent. So one of the great things is you would often convert a problem by taking the Laplace of the Fourier transform, solve it, and then you would have to invert. And the inversion step is often the difficult one. But now that we're doing complex analysis, we now actually have the tools to do those inversions. What you often would do in a differential equations class is you would have a table of inverse transforms. And you would solve a differential equation, and you would see what you would get, and you would pray that it would be in your list of, I have an inverse for you. And if it doesn't, here's the answer. And then you would hope that there's only one, that there's a unique inverse. And so what I want to do today is just give a little bit of a sense of how you would attack problems like this. And so let's say we have the convolution. So let's say h of, I'm running out of letters. H of x is going to be the integral from minus infinity to infinity of f of t g of x minus t dt. So this is f star g at x. This is the convolution. Okay. And now we define the Fourier transform of some function a is going to be the integral from minus infinity to infinity of a of x e to the negative 2 pi I xy dx. And this is the Fourier transform. So what is the first question you should ask when I write down the Fourier transform? Does it exist, right? Whenever you meet something, first ask, does it exist? If it doesn't exist, it's not really worth studying. So in probability, there's a lot of things that are nice to define, but they don't always exist, or they only exist in certain regions. The Fourier transform will actually exist as long as a is a nice function. So if a is integrable, then this exists. So exists if the function a is in L1 of R. And that means the integral of the absolute value of a is less than infinity. And note that the absolute value of e to the negative 2 pi I xy equals what? It is 1. And so if I take the absolute value of the integral, that's less than or equal to the integral of the absolute value. And since the absolute value of the exponential is 1, we get that the absolute value of a hat of y is going to be less than or equal to the L1 norm of my function a. So if the function is integrable, this at least exists. Let's calculate h hat of y. So h hat of y would be the integral from minus infinity to infinity of h of x e to the negative 2 pi I xy dx. This is the integral. X goes from minus infinity to infinity. Integral t goes from minus infinity to infinity. F of t, g of x minus t, e to the negative 2 pi I xy dt dx. Okay. So now, when we integrate this, I'm going to assume that my functions have enough decay so that I can interchange orders and however I want. I really don't have that many techniques for multivariable calculus, right? We have change of variables and we have switch orders of integration. Why might you want to integrate with respect to x first? Yes. Yeah, I can pull out the f of t. And so this would be the same as the integral. T goes from minus infinity to infinity. I have an f of t here. I'm going to write this very slowly. I have an integral x goes from minus infinity to infinity, g of x minus t, e to the negative 2 pi I, x minus t, y. Now, if I put in the t over there, I can't just put in the t, I've got to then add the t as well. And so that's going to give me an e to the negative 2 pi I ty. I'll put that over here, e to the negative 2 pi I ty dx dt. And so what we did is we added 0. But now, if I change variables, if I let u equal x minus t, what is the bracketed quantity? It is just, it's g hat where? Not of x minus t. Not of u. You might be unable to read my handwriting. G hat of y. And what's this piece now? F hat of y. So if we have f star g, that's f hat times g hat. The Fourier transform of a convolution is the product of the Fourier transforms. So this is an absolutely wonderful result. So Fourier transform of convolution is the product of the Fourier transforms. Yes. It's just what? Because when we do this integral, there's no t dependence anymore. I get to shift, I replace x minus t, I call that u, and u goes from minus infinity to infinity. This is just g of u e to the negative 2 pi I u. That's the whole reason we do the change like this. This is an extremely common technique which allows us to attack the variables one at a time. And so if I have something that involves a convolution, if I take the Fourier transform, it converts convolution to a product. Given that we're doing class after class on integrating without integrating, the convolution is defined as an integral. We are converting the integration of the convolution into standard multiplication. The problem is at the end of the day, you then have to take the inverse Fourier transform. And this is to just really provide some motivation as to why do we care so much about all of the stuff that we're doing in complex analysis? Why do we care about being able to do all these quantum integrals? It's going to allow us to solve a variety of problems. So if you've seen some things in differential equations, great stuff there. All right. And so basically, the result is that, just writing it up neatly for the notes, is that if f and g are continuous on R and they're square integrable, so they're in L2, the integral of f squared and the integral of g squared is finite, then this can all be justified. And the Fourier transform of the convolution, as I said, is the product of the Fourier transforms. Okay. Absolutely wonderful result. Okay, any questions on this? Okay, so again, if you've taken a differential equations class, how many of you have used the Fourier transform to solve differential equations? Okay, so no one has done that, but you've used Laplace transforms. And Laplace and Mellon and Fourier, just depending on your accent, they're all really the same. And so you can then ask, is there an analog of this theorem for Laplace transforms? Is there an analog of this for Mellon transforms? And the answer is yes, you can often convert from one to another. This reminds me of the log laws. The log of AB is the log of A plus the log of B. The log of A over B is the log of A minus the log of B. The log of A to the R is R log of A. Sometimes feel like, I equals -1 is a special case. There's one other log law. What is the other log law? Change of base. Excellent. Can you state it? So log base b of x. Okay, it's the log, wait, the log, what would you say, like, the log of x base a, is that what you said? At the top?
Yeah.
Okay, what's the bottom? No, almost. The log base a of b. So what this tells you is if you can do logarithms in one base, you can do logarithms in all bases. So you only need to know logs in one base. This is how you should view a lot of the stuff about Fourier transforms and Mellon transforms and Laplace transforms, that there's often ways to change variables and pass from one to another. And there's some conditions you have to be careful about. But the idea is that if you can understand what's going on in one, you can often convert it and get something else. Okay. So what I want to do now is turn to integrating a problem from earlier in the book. This is integrating the function exponential negative x squared over 2 e to the negative a plus I bx. And Mathematica is able to compute this, and it gets its e to the 1/2 a plus ib squared. So the book is, example 1, I think this was of chapter 2, calculates the integral of e to the negative pi x squared, e to the negative 2 pi I x c dx. And when you look at this integral, now that you've just had the first half of the lecture today, how should we interpret this? This is the Fourier transform. So we're taking the Fourier transform of essentially a Gaussian, e to the negative pi x squared. It's always a game as to what do you want the Gaussian's mean to be, what do you want the Gaussian standard deviation to be. The mean, there's no dispute, right? If I give you a Gaussian, what is its mean? 0. What is its standard deviation? Oh, well, there, depending on what you're doing, different choices lead to different answers. So for the people who like treating both sides of an equality, to be on like a similar standing, by putting a pi here, it's very nice. I have e to the negative pi c squared, e to the negative pi x squared. So the Fourier transform is basically coming back to itself. So the book is able to prove this identity. So how does it do that? Well, first, it actually starts with an extremely important number. The integral of e to the negative pi x squared equals 1. How many of you have seen a proof of this? How many of you have not seen a proof of this? Okay, this is something that should have been done in multivariable calculus. Now, why does that seem surprising that this should have been done in multivariable calculus? Yeah, it's a function of a single variable. Normally in multivariable calculus, you should have a function of 2 variables. So what I'm going to do is I'm going to let I be the integral from -infinity to infinity of e to the negative x squared over 2 dx. More generally, you could do e to the negative ax squared. I'm going to just do e to the negative x squared over 2. I will leave the generalizations to you. When you do things appropriately, you get e to the negative pi x squared. Or if people really want me to do a, I'll do a right now. First loud voice wins. A. All right, as long as it's a like Ponzi, then that's fine. All right, so we'll do a. So we'll do e to the negative ax squared. All right, so the first thing we do is we look at I squared, which is the integral from -infinity to x goes from -infinity to infinity, integral y goes from -infinity to infinity, e to the negative a x squared, e to the negative a y squared, dy dx. And I'm just multiplying my integral by itself. I can do this. What I can't do is I can't use the same dummy variable twice. I have to use a different dummy variable. All right, so this is the same as the integral x goes from -infinity to infinity, y goes from -infinity to infinity, e to the negative a x squared plus y squared. I'll write it as dx dy. I can shift the order of integration. If I hadn't been so pesky about actually writing down what the bounds were, I wouldn't have math. Doesn't matter. Okay. So if you've never seen this calculation before, what should you do according to multivariable calculus now when you see this integral? So if you've never seen this before, change to polar, right? So in multivariable calculus, if you have something that only depends on your distance from the origin, it's screaming at you, please use polar coordinates. So x is r cosine theta, y is r sine theta, x squared plus y squared is r squared, dx dy is r dr d theta, which you should really view as dr times r d theta. D theta does not have length. R is in meters, dr is in meters, d theta is unitless, but r d theta is going to be an arc on a circle. And so this is the Jacobian of the change of variables. And so now this is the same as the integral. Theta goes from 0 to 2 pi. Integral r goes from 0 to infinity. E to the negative a r squared r dr d theta. All right, does anybody want to tell me what the theta integral gives us? Well, 2 pi, right? There's absolutely no theta dependence, so we can just do the theta dependent integration immediately. And then we would have the integral r goes from 0 to infinity, e to the negative a r squared times a r over 2 dr times 2 over a. And so I've multiplied by 1, and I've set it up now so that if I take u equals so I'm going to do this equals, I'll do it as u is equals a r squared. So du is going to be, oh, did I put the 2 in the wrong spot? I put the 2 in the wrong spot. Sorry about that. We want it this way. I want 2ar, and I want 1 over 2a. Sorry. So then du would be 2ar dr. So this becomes 2 pi over 2a, which is just pi over a, integral u goes from 0 to infinity, e to the minus u du. Oh, what's the integral of e to the minus u from 0 to infinity? It's 1. It's just going to be negative e to the minus u. The negative sign flips the order of integration. So this is going to just be pi over a, e to the minus u, and I flip. So I go 0 to infinity. So I just get pi over a. And there's the proof. Well, this is what I squared is. So can you figure out what I is if you know that I squared is pi over a? So what would I be? Good. The integrand is positive, so we know it has to be the positive root. Therefore, I equals the square root of pi over a as positive. Now you can get a sense of why they wanted to choose a equals pi. It just makes the integration very nice. When you do the standard Gaussian, you take a to be 1/2. And then that would give you that the integral is a size square root of 2 pi. So the normalization constant for the standard normal is 1 divided by square root of 2 pi. Okay, this is an absolutely beautiful integral to do. Any questions about this? So this is actually another technique for multivariable calculus. Make it a multi-dimensional problem. Start off with something in 1 dimension, expand it upwards, and actually study it there. And the advantage of that is now we can use our change of variable formula. Okay, so how is this useful? So this is the contour that the book uses. So I'm not going to go through the proof because the proof is in the book. It takes the function e to the minus pi z squared, and it integrates it over this contour. Why is the integral of f over this contour 0? Okay, why go south? I'm not saying you're wrong. Why Grossauf? You have to tell me why I can use Grossauf's theorem. Okay. And why can I use Grossauf's theorem? You're correct. You just have to tell me what justifies the use of it. F is holomorphic. So because F is holomorphic, I can represent the rectangle as two triangles, and I can use Grossauf. Or I can use Grossauf for rectangles, or I could even use Cauchy's theorem, and there's no residues. So we have lots of ways to see that this integral is zero. And then what happens is, when we look at it, the two vertical sides contribute nothing in the limit. So in limit, this and this go to zero. Then on the bottom, that goes to the integral from minus infinity to infinity, e to the negative pi x squared dx. Right? And we know from what we just did that that equals 1. And then the top. So what does it look like on the top? It's going to look like the integral from r to minus r, e to the negative pi. And then on the top, we have z is equal to x plus ix. So z squared would be what? X squared minus c squared plus 2 I xc, right? So when I put that down here, what do I get? I get pi, and I'll have x squared minus c squared plus 2i xc dx. Well, if you think about this, I can pull out the e to the negative c squared, and I'll get e to the pi c squared, and then the integral from r to minus r of e to the negative pi x squared, e to the negative 2 pi I xc dx. And that's exactly the Fourier transform, except I'm integrating in the wrong way. Then you just bring it over, and when the algebra settles, this plus this equals 0. So when I bring it over, this equals that. The minus sign then reverses the order of integration. So now it's from minus r to r, as all integration should be. And then that equals 1. Then I just pull this over to the other side, and then is your e to the negative pi c squared. So the rest is now just algebra. But we just calculated the Fourier transform of the Gaussian. Okay. Any questions on this calculation? There's another way we can compute this. So let's consider the integral from minus infinity to infinity of e. I got to decide how I want to choose my constants. I'm going to just try to make my constants nice. X squared e to the we'll put in the pi x squared e to the negative 2 pi I xc dx. So this is what we wanted to compute, the Fourier transform, right? Let's let y equal ixc. So we would have, in a study, the integral from minus infinity to infinity, e to the minus pi x squared, e to the negative 2 pi xy dx. How should we handle this? Any thoughts? Yes, yes. And what are you doing? Right, but there's a name for what you've just done. When you're doing the quadratic formula, this is how we prove the quadratic formula, or how we often prove the quadratic formula. You've completed the square, right? It has a name. Complete the square. So this is just the integral from minus infinity to infinity, e to the negative pi. So it's going to be, I think, x plus y squared, and then minus a y squared dx. So that'll give me a x squared. So I think that works. And then that's going to just be, if I pull it out, e to the pi y squared, integral from minus infinity to infinity, e to the negative pi x plus y squared dx. What change of variable should I do to evaluate this integral? Yes. Yeah, so u equals x plus y. What do we get for the answer? We're integrating now e to the negative pi u squared, which is just 1. That's why a lot of people like integrating e to the negative pi x squared, because the integral is just 1 and you don't have to worry about the normalization factors. If you remember in multivariable calculus, if you parameterize curves and you're trying to calculate lengths or whatnot, it's much easier if you parameterize by unit speed. Because if you're always traveling the curve at 1 unit per second, then it doesn't really matter if you forget to divide by the speed, because the speed is 1. So it's just safest to do that. So we just get 1. So this is just equal to e to the pi y squared, or e to the pi iy squared. Okay. Yes. Sorry. Yeah, I was about to say, I think you only forgot 1 minus 9. When we pull out the e to the pi y squared, we have either the negative pi times negative y squared, so that's a positive. But when I'm saying it's e to the pi iy squared, I think it should be e to the negative pi. Oh, sorry, that should be c. So right, that's right. Y is equal to ic, so it becomes e to the negative pi c squared, right? If I'm letting y be ic. Okay, so what we've shown is in the special case when y equals ic, we have the value of this integral. Any thoughts as to how this helps us? So we have the integral from minus infinity to infinity, e to the minus pi x squared, e to the negative 2 pi I xc dx equals e to the negative pi c squared. And if you want, do I have to use the letter c, or can I use any letter that I want? Can I change letters? Let me put in the letter z. So what I've shown, this is true if z is what kind of number? Let's think. We needed I times c to be a real number. So I think we want z to be pure imaginary. So z is pure imaginary. So when z is pure imaginary, this is a true result. Yes? Okay, who is ready for a miracle? Now, in complex analysis, is I plus I, or is it I squared? Because if it's I squared, you've just negated being ready.
But not that.
Not that one, okay. What kind of function is this in Z? What kind of function? It's holomorphic. If you didn't want to say holomorphic, what could you have said? Analytic. Now, this is a little bit harder. What do you think is true about the function on the left as a function of Z? What kind of function is this? It's entire. Also holomorphic. So how would you prove that this is holomorphic? You could replace your Z with Z plus H, subtract, divide by H, take the limit. There is some notes in the book about how you prove integrals against a holomorphic function. This function here, e to the negative 2 pi I Z, is holomorphic. There's ways to prove that when you integrate that, you still get a holomorphic function. The book only looks at a finite interval. Why does the book look at a finite interval? You don't have to worry about convergence issues nearly as much on a finite interval when you're integrating. But we're integrating from minus infinity to infinity. We have terrific decay with the x squared. Yes?
Should we have the quality volts for either pure imaginary?
Well, it depends what you want to prove. So I'm going to use the fact that this is holomorphic and that it was this holomorphic function, and they agree along the line. So what can I now conclude? They're the same. They're the same in a bigger region. So use points of accumulation. There's a trouble with So by points of accumulation, initially we only proved this in the special case when IC was real. We now get it for free when just C is general. We no longer need it to be. So this is yet another way to integrate without integrating. We can use the theory of accumulation to, if I can evaluate the integral along a sequence that accumulates, I can then generalize my parameter. And I no longer have to just restrict myself. And the reason we do this is if I put in the IXC, this is very hard to do because I've got complex numbers, I've got my cosines and my sines, but if I split it up like this, it becomes very nice. So this is yet another way to integrate without integrating. Okay, and so we ended up putting stuff like this. All right, and so another one which I go through in detail in the notes from the previous year was looking at the integral of the function. I'll just write it out here again. So we are looking at the function integral from 0 to infinity of e to the ax cosine bx dx. And we want to study something like this. And it turns out it's better to study the integral from 0 to infinity e to the ax times cosine bx plus I sine bx dx, and then take real and imaginary parts. So if I want to integrate just e to the ax cosine bx, it's sometimes easier to bundle it and then just take the real part when I'm done. That will just give me the integral of e to the ax cosine bx. Do you think you could actually integrate e to the ax cosine bx if you had to? How would you do it? Yeah, so you could basically integrate by parts. Want to guess how often? Twice. And then bring it over. So if you do that, you can actually figure out what the integral is. I'm sorry? It is basically a Laplace. Now, when you're doing this, you have to be a little bit careful about does everything converge? So if I'm writing it like this, oh, it does actually have a minus sign. So I normally like my constants to be positive, so I'll put a minus sign here. So I want to be very careful if I'm allowing b to vary, that I do it in such a way that the integral is still going to converge. If b stays as a real number, there's no problem with convergence. Yeah, e to the minus ax is decaying exponentially, cosine bx is bounded. If b is real, the integral makes sense. But if you all of a sudden allow b to be complex, now the question becomes a little bit more interesting. Well, if we try to integrate against other things. And so the idea is that we could actually solve this and generalize things a little bit. And again, play the games with accumulation. Yes. So let me just write what these are. So cosine of theta is e to the I theta plus e to the minus I theta over 2. And then sine of theta is e to the I theta minus e to the minus I theta over 2i. Hyperbolic cosine, I'll use x, is e to the x plus e to the minus x over 2. And the hyperbolic sine is e to the x minus e to the minus x over 2. And if I want to go between them, what's the relationship between x and theta? Well, I claim that there's a relationship between cosine of theta and hyperbolic cosine of x. So if I convert, so if I take x to be I theta, they're the same. Or theta is minus ix. Now I could do it either way. And so if I ask you, what is the cosine of I theta? What would that be? It would be the hyperbolic cosine of theta. Yes. No, I mean, you would have a similar thing relating sine and hyperbolic sine. If you take x to be I theta, the hyperbolic sine of I theta is just the sine of theta. And if you take the sine of, oh, sorry. Right, you'll have a factor of I coming in there. Yes, so the signs will be a little bit different. But you can actually make sense of taking the cosine of an imaginary angle. And there's a relationship between the hyperbolic function and the trig function. And it's when you see this relationship, it's not so surprising now that you can pass back and forth between them. So I'm not going to go through the details, but as a nice exercise, if you want to try what we just did for the Gaussian, you could try looking at integral of maybe integrate e to the minus ax, and then here we're doing e to the I bx dx, right? Can you evaluate this in general? Well, in general, no. But if b happens to be maybe I times c, we can actually evaluate it. In that case, you would have the integral from 0 to infinity e to the negative a plus c, I think, of x dx. Can we evaluate this integral? What must be true about c to be able to evaluate this integral? I'm sorry? So it has to be real, but it has to be more than just a real number.
Should be less than a.
It should be less than a. So we need a plus c to be less than 0 or c to be less than a. So as long as that's the case, we can then actually do this integral. So what this means is, if I want to try to find the Fourier transform, which is, essentially it's the Fourier transform up to accent of e to the minus ax, I can first calculate in the special case when b equals ic, deduce what the answer is, and then use accumulation. And if I wanted to get the original integral, I would just take the real part. So I will leave as an exercise, putting in all of these steps to just show that you can use this idea of accumulation. If you want to do the algebra correctly, yes.
Why is the whole term?
Oh, I went the wrong direction, sorry. I had the minus sign out there. Yes, so we would want, so we would want a plus c to be greater than 0, so we would want c to be greater than minus a, because we've got the minus sign up there. I had forgotten that we had the minus sign up there, and I want the exponent to be negative. And so as long as I have the exponential of something negative, the integral makes sense, and the answer is essentially going to just be 1 over a plus c. So we can solve it in that special case. Then you say, well, because the functions are both nice, they will hold not just when b equals ic, but they'll hold in general. And so I will leave it to you to put in all the steps and just see how we can now get all of these Fourier transforms without even doing integration. So for those of you who find calculating Taylor series too much work, don't worry, we can stop even doing that.